Meine sehr geehrten Damen und Herren, liebe Kolleginnen und Kollegen, lieber Herr Professor Jungbauer, liebe Familienangehörigen, ich darf Sie sehr herzlich zu unserer heutigen Vorlesung, der Abschiedsvorlesung von Professor Jungbauer an der BOKU begrüßen. Ladies and gentlemen, dear colleagues, a very warm welcome to you here at BOKU University and all over the world. We have come together today to celebrate the farewell lecture of a dear colleague, Professor Alois Jungbauer. The lecture will be in English, but please allow me to say a few words in German to Professor Jungbauer and our colleagues here at BOKU University. Lieber Herr Professor Jungbauer, wir sind heute hier zusammengekommen, um Sie zu ehren. Sie sind ja der BOKU schon seit langem verbunden. Sie haben hier studiert, natürlich Lebensmittel- und Biotechnologie, waren nach dem Doktorat Assistenzprofessor am Institut für angewandte Mikrobiologie, sind dann in die Welt hinausgegangen, nach Japan, USA, Dänemark, Singapur, wo Sie auch Gastprofessuren hatten. Zurück in Österreich haben Sie die Verbindung zwischen Universität und Praxis gehalten als stellvertretender Direktor des ACIP, des Austrian Center for Biotechnology, Industrial Biotechnology, als Leiter eines Christian-Doppler-Labors und natürlich als Professor am Department für Biotechnologie. Meine Damen und Herren, das ist wirklich eine sehr beeindruckende Vita, über die wir wahrscheinlich nachher noch mehr im Detail hören werden. Ich möchte mich aber jetzt schon bei Ihnen, sehr geehrter Herr Professor Jungbauer, sehr herzlich im Namen der BOKU dafür bedanken, für alles, was Sie für unsere Universität getan haben. Und Sie waren, das kann man ja wohl sagen, einer der Pioniere in der Biotechnologie an unserer Universität. So wie Sie ja beim Antritt Ihrer Professur gemeint hatten, hat man das große Potenzial der Biotechnologie nicht gleich wahrgenommen. Auch die BOKU hat es nicht sofort erkannt. Das, meine Damen und Herren, hat sich ja mittlerweile gravierend geändert. Nicht zuletzt die Corona-Pandemie hat der Gesellschaft die Bedeutung der Biotechnologie ganz klar vor Augen geführt. Und die BOKU war an vorderster Front dabei bei der Entwicklung von Antikörpertests, aber auch Impfstoffen und Medikamenten gegen SARS-CoV-2. Damit die entsprechenden Wirkstoffe aber gewonnen werden können, braucht es eine ausgefeilte Technologie. Und auch die haben wir hier an der BOKU, am Institut für Bioverfahrenstechnik, wo Professor Jungbauer tätig ist. Und zwar im Bereich des Downstream Processing, also bei der Aufbereitung und Reinigung biotechnologisch erzeugter Produkte. Also zum Beispiel von Wirkstoffen, die dann in der pharmazeutischen Industrie zu Arzneimitteln weiterverarbeitet werden. Und das muss natürlich im industriellen Stil erfolgen und das ist eine Kostenfrage. Daher ist die Optimierung des Downstream Processing ganz zentral. Und auch hier an der BOKU haben wir hervorragende Voraussetzungen dafür. Wir haben das Bioindustrial Pilot Plant, eine Anlage, die bei uns zu den sogenannten Core Facilities zählt und eine Anlage, die zur Kultivierung von Mikroorganismen, tierischen, pflanzlichen Zellen dient, aber auch zur sogenannten Ernte, zur Aufbereitung der Produkte, eben zum Downstream Processing. Meine Damen und Herren, Ladies and Gentlemen, Professor Jungbauer has been one of our specialists for downstream processing for many years, and we are very curious about what he will tell us about the future of bioprocessing in his lecture now. But first, I'd like to hand over to the head of the Department of Biotechnology, Professor Matanovic.
Ja, vielen Dank. Alois, wie du mich vor ein paar Wochen gefragt hast, ob ich ein paar Worte hier vor deiner Abschiedsvorlesung sprechen möchte, habe ich natürlich sehr, sehr gerne zugesagt. Ich könnte es mir jetzt sehr leicht machen und als Departmentleiter mich sozusagen in den Erfolgen sonnen, die du mit und für das Department eingebracht hast. Das wäre allerdings nicht ganz fair nach nicht mal 3 Monaten im Amt. Das heißt, ich möchte lieber ein paar persönliche Dinge hier aufgreifen und ich habe mir vorgenommen, auf 3 deiner Eigenschaften einzugehen, die ich kennenlernen durfte über viele, viele Jahre, die wir uns kennen und die wir zusammengearbeitet haben und die dich, glaube ich, als Mensch und als Wissenschaftler kennzeichnen. Als erstes hier habe ich mir notiert, Alois ist frei von Neid. Das klingt jetzt einfach, ist aber gerade in der Wissenschaft auch gar nicht so leicht zu erreichen. Wissenschaft ist mit so vielen Rückschlägen verbunden, Projektanträge werden abgelehnt, Publikationen werden abgelehnt, Experimente funktionieren nicht wie geplant etc. Und man ist sehr leicht versucht, dann etwas neidisch zu sein auf Kollegen, die vielleicht gerade einen Erfolg haben oder einen Lauf und vieles ja, läuft offensichtlich besser als für einen selbst. Ich hatte nie erlebt, dass du dich nicht mit anderen gefreut hast über deren Erfolg und alle auch in deinem Umfeld bestärkt hast, sozusagen mit dem positiven Erfolg anderer auch so mitzuziehen und die positive Energie herauszuziehen. Als zweiten Punkt, ich habe dich immer als einen sehr großzügigen Menschen kennengelernt, was jetzt in der Wissenschaft vor allem das Teilen von Ideen und die Bereitschaft zur Zusammenarbeit betrifft. Und so konnten wir auch in vielen Zusammensetzungen ganz früh, du wirst dich erinnern, diese Kooperation in Heidelberg oder mit einer Firma in Heidelberg, die sozusagen unsere allerersten Kontakte dargestellt hat, bis zu jetzt langjähriger Zusammenarbeit im AZIP. Ein Punkt, an den ich mich auch noch sehr gut erinnere, der jetzt schon Jahrzehnte her ist, wie wir damals noch im Rosthaus das Nachbarn im Büro waren, hast du auch großzügig jedes Telefongespräch mit deinen Nachbarn geteilt. Die Wände waren dünn und das ist mir in Erinnerung geblieben. Der dritte Punkt hier, Alois ist immer heute wie damals voll von Energie, was sich in einer Vielzahl von internationalen Kontakten und Reisen zu Konferenzen und wie schon gesagt auch diversen Gastprofessuren, Gastaufenthalten an internationalen Instituten wieder gespiegelt hat. Bis heute jede Menge an Forschungsproposals, die du einreichst, wo ich nur staune, wo du immer die Zeit und Energie hernehmen kannst. Eine Vielzahl an ausgezeichneten Publikationen und was letztlich auch für die BOKU und das Department dann aus all dieser Energie herauskommt, ist eben diese internationale Sichtbarkeit. Man kann sagen, jeder kennt dich, ob ich jetzt in Taipei in einer kleinen Universität jemanden treffe oder an einer großen amerikanischen Universität, wo auch immer, wenn ich BOKU sage, kommt das Antwort, Alois Jungbauer. Und das ist natürlich für das Department als Aushängeschild sozusagen immer ganz großartig gewesen und hat sich natürlich auch in all deinen wissenschaftlichen Erfolgen wiedergespiegelt und in dem Sinne bin ich sehr, sehr gespannt. Deine Ideen waren und sind immer hochinteressant und ich bin, wie wir alle, natürlich jetzt extrem gespannt auf deine sozusagen Rückblicke und Vorausblicke in das Feld der Biotechnologie und vor allem des Downstream Processing. Ja, vielen Dank für die vielen Jahre und auch für das, was noch kommen wird. Und damit möchte ich gerne der Reingard Grabherr übergeben, die Moderation dieser Abschiedsvorlesung vornehmen wird. Danke.
Ja, danke meinen beiden Vorrednern. Ich möchte Sie alle hier recht herzlich begrüßen, das Publikum hier im Hörsaal. Man ist es ja nicht mehr gewohnt. Ich bin über seit 2 Jahren nicht mehr in einem Hörsaal gewesen, wo so viele Personen versammelt waren. Ich möchte aber auch alle Zuhörer, die über den Livestream dabei sind, auch sehr herzlich begrüßen. Alois, bevor ich dich ankündige, möchte ich vielleicht, es gibt jetzt gar nicht mehr viel, was ich dazu sagen könnte. Deine Vita wurde hier eigentlich schon gut dargestellt. Was ich vielleicht noch sagen möchte, dass du einer der motiviertesten und motivierendsten Lehrer bist und warst und weiterhin bist und auch ein sehr umsichtiger Mentor. Und das ist ganz, ganz wichtig für deine Kollegen und das war es auch für mich in der Vergangenheit. Dafür danke. Außerdem bist du natürlich, und das haben wir jetzt auch schon gehört, mein umtriebigster Kollege. Wir haben es gerade gehört. Man hat das Gefühl, du bist überall auf der Welt gleichzeitig, egal wo man hinkommt, was Konferenzen betrifft, Organisationen, Publikationen, du bist Editor und so weiter. Und du bist für jeden Spaß zu haben. So with this, ladies and gentlemen, I would like to mention that after the talk by Professor Alois Jungbauer, there will be the possibility to ask questions, not only here in this lecture hall, but also from the live stream. We will collect these questions and then I will read them and we will ask for answers. And with this, I will give the stage to Alois and we are looking forward to hear about whether current bioprocessing is fit for future or not.
So, sehr geehrte Frau Rektorin, lieber Didi, besten Dank für diese sehr netten Worte und es ist auch motivierend, wenn er auch sagt, auch ich muss motiviert werden. Ja? Wenn man von seiner Organisation, eigenen Organisation nicht wahrgenommen wird und nicht unterstützt wird, kann das in Frustration enden. Hallo? Ah, sorry. Dann kann das in Frustration enden und dann arbeitet man in einer Organisation, wo jeder unzufrieden ist. Ja. Und dafür möchte ich der BOKU, den Department und auch den Kollegen und meinen Studenten danken. Aber ihr bekommt noch am Ende meiner Vorlesung ein paar schöne Fotos und Folien von meiner Karriere. Now I want to switch to English and talk about the farewell lecture, Abschiedsvorlesung, and it's really difficult to find the right tone. We have people who are not really in the field of biotechnology and downstream processing. We have a lot of experts. So to have a mix between a superficial talk or an overview, not to be superficial, and the details. So. And actually, it's really clear what's about our future, because we have to really think about, because our world is currently in a transition with the climate change, but also what's going on with war in Ukraine, the supply chain limitations, and so on. So, sorry, I forgot to welcome 2 of my colleagues. Suichi Yamamoto from Japan, yeah, he said he will join live, yeah, so welcome Suichi, yeah, and also Giorgio Kata from University of Virginia, yeah, so both of you will miss afterwards the drinks and the real good discussion, yeah, so that's, thank you for joining virtual, yeah. So, with this interruption, I will continue. Is minimizing, so the future will be minimizing the impact on the environment, yeah? And then we have two extreme production scenarios. So one production scenario is flexible. So we want to produce our material everywhere in the world. You heard about that the pandemic vaccine should be produced in Africa, in Asia, at smaller scale. Yeah? We have still not yet solved this problem. And the other thing is the large-scale manufacturing. Recently, you may have heard that Boehringer Ingelheim has launched a gigantic manufacturing facility here in Vienna, but also recently Sandoz or Novartis has also launched a fourth gigantic manufacturing facility in Schaftenau. So we have really two extreme scenarios, and I will guide you a little bit through this. Maybe some of you who were at meine Antrittsvorlesung, so when I started, I talked about the product classes in biotechnology, and we have to actually think about biotechnology in the context of product classes, which range from 2 nanometer, what is like an insulin, over antibodies, virus-like particles, viruses, and also cells. Yeah, because meanwhile, cell therapy became a very interesting option for biopharmaceuticals. And then here, what came up recently in the past 2 years, what you see here, this is at least a theoretical depiction of our SARS-CoV-2 lipid nanoparticles, so this biotech Pfizer material. And so you see, because I have drawn this to the scale, yeah, is in the same range than our viruses or virus-like particles. The other thing is about this typical or this wide range of product classes. We have to ask ourselves, what is a typical dose? And when we see what is a typical dose, we also find out the power of biotechnology. Now is when you see this Comirnaty, this SARS-CoV-2 vaccine, is 12 microgram absolute for an adult is the dose. Yeah? So this means for 3 billion people, we only had to manufacture 36 kilogram. So 36 kilogram for actually global demand. Yeah? And here I think we have one problem. We have a problem of communication of science and technology. Because the general public does not realize how efficient biotechnology and biomanufacturing is. Yeah? The other extreme is when we go to gene therapy vectors, antibodies. So we need about 10 to the 12, yeah? So gigantic amount of viral genomes per kilogram. Yeah? So when we try to actually administer this intramuscular, or quite a lot of cells for cell therapy. Yeah? So again, we have the extreme scenario of manufacturing size, but also the extreme scenario of manufacturing doses. So, and then this actually determines our manufacturing scenario. We may have blockbusters, yeah, with a high dose and high patient number. For instance, our antibodies, high dose and low patient numbers. So this is actually a critical thing because nobody wants to touch this because you can make actually really money out of that. Then we have low dose, high, extremely high patient number, and this is this typical new lipid bio-nanoparticle vaccines. And then we have orphan diseases and cell therapy, where we have quite often a very high dose and a very, very low patient number. And this actually can be only managed with the support of the general public. So, just to see how diverse manufacturing in biotechnology is. Yeah? So how can we now compare the quality and how can we compare the impact, what I mentioned on environment? Yeah? And there is a quite interesting metric which is called the process mass intensity. The process mass intensity is the total input mass in a process step or in an entire process divided by the mass of the product. Because if you calculate the cost of goods or the investment costs, all these type of things, this is not universal, because it depends on the size of the company, the purchase department, and so on, so a lot. But 1 kilogram is 1 kilogram in Austria, in New York, in Japan, and so on. So we have a global metric. And then this is quite interesting. For a monoclonal antibody, a typical, actually, biopharmaceutical, 60% of all our biopharmaceuticals are these antibodies. We need 7,700 kilogram per kilogram process mass intensity. Think about 7 tons to produce 1 kilogram. Yeah? And 94% of them is water. Yeah? So, and then I think chromatography or separation, you mentioned, thank you, you already introduced the separation science. Yeah? Of this 94%, 60% of the water of this water consumption is chromatography. And when we want to optimize, actually, we have to turn this knob, which actually responds really a lot, not the tiny ones. Yeah? So that's really important. So therefore, it's clear that we have to reduce our water consumption, and hereby we can then actually improve also our actually process economy, the footprint, and so on. Recently, we have also developed what is called the water-related impact of energy, the Varian, as a metric, which has been really well received. And here we see actually the impact of bioprocessing on our CO2 footprint. Because water is the major, actually, driver of our environmental footprint. Yeah? Also, the major driver of the CO2 production is through water, actually, production and water purification. So, when you see here, in a conventional system, we have about 60 to 80 kilogram CO2 per kilogram antibody. So, and then you see the power of when we optimize this. If we go to 500 liter, what is called fat batch, yeah, an improved system, yeah, we can already reduce to this to 20. And then maybe also actually a discussion on this carbon tax, yeah, because from the water-related costs, yeah, per kilogram API, yeah, only a minor fraction is the carbon tax, what you see here. So, for industry, yeah, honestly, the carbon tax will not be an incentive to improve something. Yeah, that will not. Maybe it will help us, yeah, that we get a little bit more income, yeah, to support research and technologies in the field of environment, yeah, like what EU does, yeah, these huge programs, yeah. But the incentive to reduce actually the environmental footprint is the economy. And just also put this in perspective, for 1 kilogram beef, we need about 15,000 liter water. Yeah? For 1 kilogram antibody, about 7,000 liter water. We need about 60 kilogram of, produce about 60 kilogram CO2 per kilogram beef, and about 20, so in this order of magnitude CO2 for antibodies. So now, actually, how can we, and I want to explain you how can we reduce actually this environmental footprint for the future, that to become really fit for the future. And in chromatography is this the race for dynamic binding capacity. So this is the capacity in chromatography when you actually load your product on a chromatography column. And you see here in this race for dynamic binding capacity, a lot of companies have started to develop new products. One is the DAE Cephadex, has been actually developed 40, 50 years ago. They had a very high capacity, but what is called a low residence time. So you had to operate very, very long time. So one step took a week or so. Nowadays, they have reduced this and kept the residence time very short. So with actually chromatography, and we can, what I mentioned, can reduce by increasing dynamic binding capacity the buffer consumption. With the buffer consumption, we reduce the BMI, and also synchronously, we actually improve the economy. And so how to reduce the BMI? And actually I have here, we have Suchi here online, yeah. We could improve the column utilization, either by a velocity gradient or a countercurrent loading. We sold this technology of velocity gradient during loading productivity for free. And this could be also a strategy for the future, not only in downstream processing, also in other actually disciplines, that we put in more intelligence in our product, in our processes, because this doesn't cost anything. We only become smarter. Or we could do the buffer recycling, or what we have developed over the past is this alternative capture. So the improvement of column utilization. And here I have a picture of our book, which I have written together with Giorgio Cata. It is in chapter 10. Yeah, I took out this picture. It's the improvement of column utilization. So usually you work with one column, one chromatography column, but you want to have actually when you work with more and actually interconnect them in a smart way, then actually you can really improve the productivity, yeah, and together also reduce the water consumption. So I have to show you something. So what is the countercurrent loading? Think about, yeah, you have water, and this is our chromatography column, yeah, so that's our, so you load this chromatography column until water goes out here. Then, if it's fully soaked, yeah, you would actually waste your product. So if you actually then collect your product on a second column, yeah, then you can soak the first one fully, yeah, then take the first one, squeeze it out, and then once it's finished here, you go on here and here and here and here. And thereby, actually, you fully utilize actually the capacity of a chromatography column. And so hereby, and this is the most, one of the most efficient ways, and industry is really doing this quite a lot. Yeah? And so what we have shown, actually, when you go from a typical conventional process, yeah, to this periodic countercurrent loading, so to reduce, actually to fully optimize the system, you can come from about this 7,000 kilogram per kilogram antibody to about 2,000. So already a substantial improvement of the environmental footprint. So we did this for different scenarios, for 1,000 kilogram product, a blockbuster, a smaller product, or even a larger product. The other thing is what we have recently done, and hopefully we can really spin off a company from BOKU in this field, yeah, is actually a single-use device for development of solid feeding. Yeah? In interest of time, I actually have reduced this this part to only 2-3 slides. Yeah? When you think about, we could reduce already the water. But when we prepare the buffers, the media, and so on, we have to think about that about 2% or 3% of our media and buffer is the solid. The rest is liquid. So when we actually on demand produce the buffer or the media, we already save a lot because we never will actually prepare buffer or media in excess. We always only will actually produce as much as we need, and we don't ship water. So this is actually one of PhD students developed this, Daniel Komutsky, with a single device development and with funding, prototype funding. So this is the prototype for really on-demand, in situ preparation of buffer and media. And by doing so, actually, you can furthermore actually reduce size, the floor space. You make it even more environmental friendly, and actually you can automate it. And our idea is, in future, you may have, and those of you, my students, all had to prepare buffer in the morning. So you remember, and this is very annoying. You have to filter it, you have to degas it. So then later on, the rest is fun. Once you go in industry, it's different. You have technicians, they work for you and they do it, and you just order it. But as a PhD student or a master student, you have to do it by yourself. So the idea is like the coffee machine. Actually, you prepare together in your chromatography workstation your buffer on demand. So it's like the black coffee with sugar, without sugar, and so on. So the phosphate buffer, the tris buffer, whatever you do on demand. And think about that. You see, okay, this is some curious idea. It's not curious at all. Because we did like a preliminary economic analysis. The global saving of media and buffer is about $2.8 billion per year. And this does not take into account actually the laboratory work and the pilot scale work, because this is very difficult to estimate how many people or labs produce buffer and media in excess. Because those of you, and I know a couple of my former PhD students, which actually complained about a chromatography column which ran dry. And once your column ran dry and you wasted your experiment, Christa, don't laugh, that's true. These things happen, when it ran dry, you always then prepare really the buffer in excess. Instead of 300 milliliter, which you calculate, you do 3 liter. And if thousands or 10,000s or 100,000s of lab people, and they do it, in excess, this is a huge multiplier and also an impact. So here we think we are so conservative, we have to prepare, we have to do the buffer by ourselves. Instead, letting do it by a machine. Because we don't prepare our antibodies and our test kits by ourselves. We also let it prepare by a company, by a machine, and we order it. So now let's go to the next step. If we have the case, not biopharmaceutical production, because we want to, are we prepared for the future? Recombinant protein or food. Nowadays, a lot of companies want to have actually proteins, animal proteins, which are not produced in animals, so that you can actually sell it as a vegan food. So, and then, for instance, casein is a typical example. So here you see the annual casein production in Europe. And all of a sudden you see the completely the difference here in these industry sectors. About 180,000 tons per year in Europe. Yeah, so it's a completely, not kilogram, you see, not 30 kilogram per year, yeah, it's 180,000 tons, yeah. If we assume 30 gram per liter, no losses in recovery, and we would produce 1% for food purposes, yeah, by recombinant DNA technology, we would require 60,000 cubic meter fermentation process. With a selling price currently 25 euro per kilogram, and an optimal theoretical BMI, you could not put, become better, is 33 kilogram per kilogram. So that would need enormous amount of water. And so you can get the feeling, in this case, we are not really prepared for the future. The other thing is the cultured meat. 37% of global protein supply and calorie supply is by meat and dairy products. Yeah? So, and they consume a lot of land, yeah? But we are short of land. So what you can do, you could do cultured land. In Singapore, they have already done it, but they have already done it for a completely different purpose. Yeah? And this is actually their own safety. So because Singapore, and I actually lived in Singapore and traveled back and forth between Singapore and Austria. Singapore is actually ruled by military people. Yeah? And their great concern is that they cut off ones, yeah, from Malaysia and Singapore and don't get the food anymore. Yeah? They have extremely high military expensive, but they also have a very strategic thinking. In this respect, we have to actually, I think I laughed 2 years ago about when they did these things. Yeah? But now, actually, in the current situation in Europe, we have to think about our actually safety issues, yeah? So that we have really a strategic thinking. Yeah? So we are dependent, I don't want to reiterate this, yeah? And a lot of natural resources, not only gas, nickel, all these things, yeah? on Russia, yeah? And we were not prepared. Yeah? And I actually, in this respect, we are also not prepared. We are not prepared for actually a complete shortage of starch or grain. Yeah? So I'm not sure if we could actually solve this with biotechnology, but it could be a contribution. I liked actually this quite well because that said good or go out. Yeah, so that's. So, and then cultured meat, you see, if we do this, we have made, and this is still in my interest, yeah, so that's is in my interest, how could we do the cultured meat? You have a continuous production, you in mammalian cell culture, you do a meat slurry, you produce a meat slurry in a drum or whatever, and then you have to recycle this, yeah, and you can feed with soy protein our actually mammalian cells. Yeah. We still would need a soy protein to get cultured meat. So the question is then, do we eat the soy protein or eat we cultured meat? So there's a different thing, but what you see here is the theoretical BMI is 300. Yeah. So this is still quite a lot. Yeah. So at the end, I will talk a little bit about the upcoming therapies. Yeah? So this will be gene therapy and vaccines, yeah? Lipid nanoparticle and cell therapy. Didi, you already mentioned about the internationality and the visibility. Yeah? And actually, my impression is that BOKU does not really disseminate their results and their competency. And I am sure as a rector you agree to that, yeah? And also Didi, you know you agree, because you are also very international person, associated with the European Federation of Biotechnology, editor, and so on, yeah? So, think about MIT. If they would have invented the packaging of these lipid nanoparticles for the Pfizer-BioNTech vaccine, they would have saved the world. And if it's done together with Harvard University. At BOKU, 2 scientists, especially, have invented this. Yeah, they have invented this. Then has been transferred to the company Polymoon. But the world does not know about. Yeah, so that actually a really essential part of these technologies come from this house. Yeah, so, and here actually my heart bleeds, yeah, that we don't do more for us. Yeah, so the gene therapy, there could be like these lipid nanoparticles. There will be not the vaccines alone. I think a huge thing will be the cell reprogramming. So it's a completely new way to actually cure or treat cancer, for instance. So you inject these lipid nanoparticles with a little bit RNA or DNA, and then the cancer cell is reprogrammed into a normal cell. Yeah, so this is possible, has been shown. So therefore, this technology has a huge impact. And then also with Reingard, our beloved extracellular vesicles, but we have to go also to intracellular vesicles. I think we did a lot already on vaccine manufacturing, but once we go from vaccine manufacturing to gene therapy, we have the problem that we need enormous amount of particles. And the other thing is, when we do this vaccine manufacturing, that we have a lack of monitoring. Here you see a high-resolution electron micrograph. Yeah? This is actually a virus-like particles, but these are aberrant particles. These are other ones. Yeah? They look quite similar, yeah, in this high resolution, but it is really difficult to distinguish them, because such electron micrograph is very time-consuming. You cannot do this on a routine basis. And therefore, I will show you what is the problem. So, how can you, we have here these eggs, yeah? You have these eggs, yeah? We have these eggs. So, if you look on these eggs, you see, it's difficult. Yeah, what is this egg? So, this egg, great, yeah. This egg, no, it's just, maybe it's different. It's different sizes, but it's very difficult to separate them, yeah, and to actually online monitoring these eggs. Yeah? So, what we do with these eggs, yeah, what we could do with these eggs, sorry, I have, with these eggs, you can actually look into the eggs. So, so you see, one is a surprise egg, the other one is a real egg, it's a cooked egg, but actually you cannot do this. So last week I went to the radiologist, yeah, and this also reminded me, because I have a lot of foreign students from Portugal, Spain, Brazil, and so on. They try to learn German, yeah? And to understand actually the language, you also, you cannot only learn the vocabulary, you also have to understand the language in context. Also, I know my granddaughters are raised bilingual, English, German. So if you have to actually translate Linse, you could do lens or lentil. Yeah, suppose it's Linse. So you know the context. So I went with my daughter to the radiologist And then when you come into the reception and you say, ich wäre da zum Eierröntgen. So that's you have to know the context, yeah. So if you don't know the context, yeah, that's really the problem, yeah. So and then we did the Eierröntgen, yeah. I didn't take off my trousers, yeah. So that's we did the Eierröntgen, and then you see. But you see, we still, with this, we could not really distinguish them. Yeah, that's, so you see here, when I uncover them, so we have an Überraschungsei, we have an egg, we have another egg, yeah, Löffelei is called Löffelei, yeah, and then we have another egg. But here you see the problem, and I don't want to make a mess here. Yeah? And Monica, my wife, she has actually marked it, because one is cooked, boiled, the other one is raw. Yeah, so we don't want to make the, yeah. So, but you see, even here in the X-ray, you could not distinguish between these different eggs. And this is actually really a huge problem what we currently have in this bio-nanoparticle purification and also production, yeah? Because we want to actually see this. And if we need a lot of time and effort, yeah, to analyze this, this gets very costly and also very time-consuming. So we have one method, yeah, just to show you. This is this nanoparticle tracking analysis, yeah, and here you see these actually virus-like particles in this type of microscope, where they actually are counted, how many are, and actually how big they are. Yeah? But still, in this technology, they could not distinguish between this and these eggs, yeah? Because they count the size, yeah? Or they measure the size and count the numbers. We are interested in virus-like particles, this a lot, because it had shown recently also a group in Israel that these virus-like particles can be also used for gene transfer, yeah, as delivery vehicles. Now, a couple of last slides. Have we reached the physical limits for this purification? And I think not. So this is a typical chromatography where you have the specific permeability and the monoliths. So the particles are too big, the virus-like particles for the beads. Maybe they are good for the monoliths, but we have non-woven membranes. And the non-woven membranes is actually a mesh of membrane, yeah, where we can load these particles, they bind and can be eluted. Those of you, so these are our recent results with these non-woven particles, membranes. We can load a lot, we can wash, we can elute, and then we are really able to kind of separate these different forms. Yeah? And when we benchmark our process with these non-woven membranes, we could really increase actually the capacity by at least 2 orders of magnitudes. And then what we are also currently doing, and we have also applied for a patent in this field, is actually that we use monoliths, ion exchange monoliths, 3D-printed material in the range of 5 to 20 actually micrometer, really to have, instead of a non-woven membrane, a geometric material. So let me now conclude. Fit for the future. For protein pharmaceuticals, I am not so concerned, because process intensification, reduction of water consumption has been realized. Optimal productivity is not optimal economy, but not lowest footprint. This is understood. there is a certain burden of change that the industry is reluctant. Why should we change? They need a pressure from outside. For protein, for food and cultured meat, I think the processes are not yet sustainable. I think to some extent it's wishful thinking, and we are not fit for the future. For biopharmaceutical production, we need better process analytics, we need improved processes, but the good thing is we can apply the same strategy as for proteins, and the manufacturing scenario is high dose, except those once we go for actually these nanoparticles. Yeah? So I think this is my conclusion is mixed. In some industry sectors we are fit, in others we are not fit for the student. Yeah? So now it is really difficult to actually say thank you, because if you actually start to mention names, I forget somebody, yeah? And I don't want to forget somebody. Therefore, I want to thank my students, my colleagues, my rectorates, my technicians, my administrators, my institute heads, my department chairs, my family, wife and friends, and also my teachers and taxpayers. We always forget about this. Yeah? No, we forget it. We are a public institution, and we have conveyed this message to our taxpayers and politicians, what actually we have accomplished. And quite often we are too shy to tell about these things, yeah? Because they actually also have to justify where should we put the money. Should we put the money into an institution which has substantially contributed to a vaccine which helped actually to ameliorate actually the pandemic, or should we put this money somewhere else? Yeah? I think this is a really, really important question. And then I already mentioned in the foreign people I mentioned by name, František Svec, yeah, he was in Prague at the Institute of Macromolecular Chemistry. He was one of the inventors of monoliths. I met him already in the year 1982 in Prague, and then he went through via Germany to Berkeley. Then Giorgio Cata, I actually went along with him for many, many years, and still I go along with this chromatography course and conferences. And Suichi Yamamoto gave me the actually opportunity, also his similar age, to really learn chromatography, because he is one of these very, very early pioneers in this field. Yeah? And then we have a lot of companies and institutions I have worked over in the past, and still I will continue to work with them. And then here you see then now a couple of pictures while we maybe answer questions. Yeah? So, or not only questions, I have to defend my hypothesis. Yeah, that's. I have not a picture. Yeah. So that's the main. Maybe some of you. Good.
Okay, thank you. Thank you very much, Alois, for this very enlightening presentation. So if you're now ready for your defensio, then...
I'm ready for the defensio.
It's your turn, either here in the room or from the live stream, to ask questions, tricky questions. So maybe I start then. Yeah. Now, it's probably a stupid question, but why can this water not be recycled?
I mentioned about the companies are very reluctant when you recycle the water that you also recycle the impurities. And you have a build-up of impurities. Yeah? And if you purify the water, from the buffer or the media, then it gets way more expensive. Yeah? What is currently done to use water streams for others, so for other purposes. Yeah? Or recently we have heard a quite interesting idea this week. Yeah? A group in Ireland, they they use the cell culture, the spent cell culture media, yeah, for CHO, to actually cultivate E. coli.
Yeah, that's a good idea.
This was really, yeah, and it was, why didn't we have this idea? That's really, yeah, yeah.
So, questions?
Did it?
Yes.
Yeah, so.
Alois, you said at the end that, in your opinion, biopharmaceutical manufacturing is fit for the future because the major problems have been solved, if I summarize. Does that mean that research in this field, let's say the exciting part has been done already, and what is left is more like tweaking and small optimizations, or is biopharmaceutical research fit for the future?
The research is fit for the future. The biopharmaceutical, maybe then this, thank you for asking this question, yeah? The research is fit for the future, yeah? But you see, what we constantly have to do is, yeah, for instance, to improve our production data, yeah? And there, we are still not there. Yeah, we are not yet there, so we can do more, because if we produce twice, 3 times, 5 times, yeah, the amount, yeah, we would actually reduce our environmental footprint almost linearly. Yeah, so that's fit for the future. I meant. Like in the field of food, yeah, to replace food by biotechnology, yeah, we are not fit. This is wishful thinking. Does this clarify my? Yeah?
Okay. Nicole.
Na? Die Frau.
Ja,
okay.
sie war zuerst da.
Maybe it's a stupid question, Alois. Did you ever eat any of the meat slurry?
I have not yet eaten. Yeah, so that's yeah. But if you have a nice, like in Singapore, a nice sauce, a spicy, a curry, so it doesn't. If you have a chicken or a crocodile or an ostrich, yeah. So.
Since my original profession is a law professor, I'm curious about your opinion on the legal framework for biotechnology. Do you think this is fit for future, or is it too tight, or do we need some regulatory sandboxes where we can have a room, a space for more freedom under a controlled circumstances?
Actually, I was involved. I was a young assistant professor when we had the discussion about the Gentechnikgesetz. Yeah, I was actually sent to the Ministry of Science at that time, and the minister was Mr. Busek. Yeah, so at that time when we had this discussion, yeah, about the Gentech. I think, meanwhile, this is a very, especially for this, is a very good legal framework. Yeah, the companies, we feel comfortable about these things. Yeah, I cannot really comment on the legal framework in the field of recombinant plants. Yeah, this is still a very, very, very critical thing. Yeah. I will think about this question. Spontaneously, I cannot say yes or no. There would be actually a necessity really to change something, to implement new things. Yeah.
Okay, any other questions? Do we have any questions from the live stream? Many greetings. From Brazil.
Is Igor Bresolin, or who is from Brazil? Huh?
I don't know the name.
You don't? Then, okay. Huh?
Florian, bitte.
Alois, thank you very much for the great presentation. We've spent approximately 40 years together at this department. What do you think will be the situation in another 40 years from today?
That's very difficult to say. The 40 years today. I think when we started, it was the really revolution about gene therapy, genetic engineering. So that all of a sudden you could produce something. The nice thing was actually at that time our head of Institut, Hermann Kattinger, realized this immediately, that we have to go to this into this direction. I think for the upcoming next 10, 15 years, we should not overlook about these nanoparticles, mRNA, and this type of technologies. Because in the pharma industry, this will actually is already taken up. They don't speak about this because they don't want to actually make their competitors alert about an upcoming technology. So this will be the next 10 years. What will be definitely different in future, I don't know if it's in 40 years, but in 10 years, 20 years, that we come closer what chemical industry is doing now. So that the process described by, we call this digital twin, that we have actually designed the process maybe to much greater detail in silico, this type of things. If we ever come up to replace some of our actually nutrition by biotechnology, that would be quite difficult to say. But it could be possible. Definitely where Didi Matanovic and his colleagues is working, what I believe is, and this is fit for the future, where you are, that doesn't mean that you need no research, but you are fit for the future to actually produce chemicals with CO2 as a nutrient. Definitely, that's something which will come, needs a lot of research and a lot of efforts. That, I think, will be definitely.
Okay, Alois, there is a question from the live stream. So someone is asking about your opinion to the future of membrane absorption to replace chromatography and reduce water consumption.
Okay, my thing is in the field of this virus-like particles, viruses, vaccine manufacturing, this membrane adsorption and non-woven membranes and so on will definitely be used. I'm not sure if this will be the solution for the protein manufacturing.
Okay. Okay, Rainer.
When I read the numbers of water consumption for 1 kilogram of beef, why should I think about reducing water consumption of chromatography? This is ridiculous. I mean, when you compare the numbers, there are trillions of tons of beef.
This is trillions. So you are right. That's the global thinking. But the other thing is, if we reduce the water consumption for antibody production, our process gets more economic and more sustainable. So this is the incentive. We will not actually solve the water problem by reducing our water consumption for antibody production. You're right. So completely. It was only also to show where we are approximately.
Okay, we have another question from the live stream. Please comment about reducing the costs of biopharmaceuticals. Will improving process actually make these drugs affordable?
I don't know, because everything is recorded and can be found on
Used
the internet.
against you.
In the internet. We have to say, and this is the firm opinion, my firm opinion, there is not direct correlation between drug price and manufacturing costs. The drug price is determined, you charge as much as it is possible, as much you can get out of the market. This is the reason why the drugs are more expensive in the United States compared to Europe. Because in the US, the insurance companies are willing to pay this, because they upload then these expenses to their actually clients. Yeah? In Europe, we have a public health system, and which is actually opposing against higher drug prices. Unfortunately, I have to say this. And whenever I write a research proposal, yeah, of course I write into by improving process economy, we will get affordable prices. Yeah? But with the, let's say, latest generation products, this is not the case. Yeah, that's, yeah. For mass products, definitely.
Okay, now I have a really important question. Dear Alois, now we know the future of bioprocessing. Can you tell us something about Alois' future?
I think this question came from Suichi Yamamoto. What do Rainer, agree? Yeah, that's my future will be visiting you in Ube, for instance. Yeah, having a nice Japanese food. Yeah, a sashimi, for instance. Yeah, that would be my future. My future will be also enjoying science, enjoying family and friends.
Enjoy. Okay, there's one more question, I think, from the live stream. There is time in between. Someone else here wants to say something or ask a question. I think you explained everything in
okay, good. No,
very, so people can really see and understand. Okay. Okay. Can you comment on good models to predict the economic benefits to go for new innovative solutions for production processes and to convince the industry on a long-term basis?
Actually, what we have done with the economic modeling, we used a software which has been developed by a company in UK, Biopharm Services. Yeah. It's called Biosolve, and this software has the big advantage of a huge databases, yeah, so that you don't have to actually get all these economic parameters, the costs and cost functions by yourself. Yeah. Then one of my students, Alessandro, has programmed a very nice Monte Carlo simulation. So together with this, you can do this, and we get also quite a lot of inquiries from industry to actually calculate their costs. Yeah, that's,
Okay, and here we have the last question. Thanks for presenting the insight on water consumption. Have you ever compared the costs of water production and disposal for stainless steel facilities in comparison to production of disposables?
We have done this, yeah. We have made comparisons, stainless steel and disposable. This depends a little bit on the manufacturing scenario. So when the manufacturing is smaller, yeah, then the disposable will win. Yeah. If the manufacturing scenario is big, the stainless steel will win. But you should not underestimate in stainless steel facilities we have to use a lot of organic acids, inorganic acids, and sodium hydroxide. And both these acids and bases are actually very energy intensive when they have to be produced. That is often overlooked.
Okay. Okay, dann vielen Dank, Alois. Ich glaube, du hast es alles sehr anschaulich erklärt. Und es war eine würdige Abschiedsvorlesung, ohne dass du jetzt wirklich weggehst. Und ich bitte jetzt unsere Rektorin, Frau Professor Schulew-Steindl, um abschließende Worte.
Dann sitzt sie da. David.
Ladies and gentlemen, I think first of all, Professor Jungbauer needs a very big applause for this great lecture.
Thank you. Yeah.
And I think we can very well understand now why you're so popular with your students. So you demonstrated everything so tangible and practical that leaves good impression, I would say. So we had a very interesting and also entertaining lecture on the future of bioprocessing. And I can assure you that BOKU University will do its best to make bioprocessing and biotechnology fit for the future at our university. As you probably know, our motto in this year is featuring future, or in German, nachhaltig vorausschauen. Why? This is because BOKU University celebrates its 150th birthday this year. And we have all the competencies that are needed to be fit for the future. Since we have been researching on all these topics for a very long time, for 150 years. In 1872, BOKU was founded as a small agricultural and forestry university. Today, it has developed into one of the leading life science universities in Europe. And we will celebrate our anniversary properly. The highlight of the year will be our future conference on May 24th, 25th in the Aula der Wissenschaften, the Aula of Sciences, here in Vienna. And there we want to deal with many exciting topics that are very relevant for us and for the society as a whole, and that shows our diverse competencies which we have here at BOKU. I just want to mention 3 of these issues we want to deal with. Food security, climate-friendly mobility, and the challenges of energy transition, and more generally the question of how to shape the living spaces of the future. At our future conference, we not only want to explore these topics scientifically, but also we want to present them in a comprehensive way and bring them out into the society. Ladies and gentlemen, I invite you already now very warmly to this future conference. It is open to everybody. But now, my dear Professor Jungbauer, let me thank you again for your lecture today and for everything you have done for BOKU University during the past years. And on behalf of BOKU, I would like to wish you all the best for the future, be it in Japan or wherever in the world. And please stay connected with your university. Ladies and gentlemen, thank you for watching today's lecture, for being live with us via the internet and live here in the conference room. And thank you for your interest in BOKU. And all the best to you and greetings from Vienna.